Hello students, welcome back to the computer science class of PUC second year. Okay, so in the last session we started with the third chapter, that is logic gates. So what all things we studied there? We studied what is a logic gate, types of the logic gates, which are those types. Types of logic gates are mainly of two types. One is basic gates, another is derived gates. So in the basic gates we saw three types of gates. Which are those? Those are NOT gate, OR gate, AND gate. Yes, so now moving on to the next category of gates, that is a derived gate. Then what is a derived gate? Name itself suggests derived, in the sense these gates are made up of using the basic gates. Okay, using all those basic gates, NAND, AND, or not, using these three basic gates we can form other gates. Okay, those are nothing but derived gates. Means what? Using the basic gates we can derive derived gates. Okay, the first one is NOR gate. Okay, see, NOR gate, name itself suggests it is a combination of OR and NOT gate. NOR is a combination of OR and NOT gate. This gate also has minimum two inputs. This gate also requires minimum two input signals, and it produces only one output signal. Yes, all the gates are producing only one output signal. Yes, but they can accept two or more inputs. Okay, so this gate is also accepting two or more input signals, and it is producing what? It is producing one output signal. Yes, see the diagram, logic gate diagram. You can see here, this is a OR gate. Yes, in front of that OR gate there is one bubble, that representing what? That is representing a NOT gate. So this gate is a combination of OR gate and a NOT gate. Okay, see what is the behavior of this gate? When will be the output is 0 and when will be the output is 1? As I said in the last session, 0 means it is we are supplying low voltage, 1 means it is we are supplying high voltage. Yes, okay, now see, if all the inputs are 0, then only the output signal is high. Means when you supply here 0 voltage at this input signal, then only we are getting output as 1. Okay, see here, for one input signal we are supplying how much? We are supplying 0. Another input signal we are supplying 0. Means both input signals we are supplying 0 voltage, that is a low voltage. Then the output signal will be high, that is 1. Okay, now if I change here, one input signal if I keep as 0, another input signal if I keep it as 1, then what will be the output signal? The output signal will be 0. Yes, so we will check for another combination. First input signal I am giving as 1, second input signal I am giving 0. Then what will be the output? Output will be 0. Yes, now if I give both input signals as high, then what will be the output? Output will be 0. Yes, means how is the behavior of this? The output will be high if and only if both input signals are low. Yes, if any one of the input signal is high, then output will be 0. This is exactly opposite of OR gate. Then how is the truth table of this? Okay, we will see next. See here, we have two input signals. First one is, assume this is X. Okay, second one is Y. The output will be what? X plus Y. If I use only this much, this becomes a OR gate, OR operation, right? So what we are doing here? It is a combination of OR and NOT. NOT means we have to give a bar, that is nothing but complement. Yes, now see the truth table, that is here we have two input signals, one is X and one more is Y. Okay, so as I said, how can we take these combinations? If two input signals are there, means 2 to the power 2, means total how many inputs I can give? In the 4 combinations of inputs I can give, that is starting from decimal number 0, 1, 2, 3. Okay, so how I am representing 0? That is, one input signal is 0, another input signal is 0. Okay, what will be the output? At that time output will be 1. Yes. Now if I give any one of the input signal as 1, see here in the second combination, here I have one input signal, here I have one high input signal, and here I have two high input signals. So whenever we have high input signals in any one of or both the input signals, that time we are getting output as 0. Yes, so what is the behavior of this gate? This gate is going to give output as high only when both inputs are low, that is 0. Otherwise, if any one of the input signal or both input signals are high, then output is 0, that is low. Yes, this we saw for a 2 input NOR gate. Now we will see 3 input NOR gate. 3 inputs in the sense, how many input signals are there? 1, 2, 3. That is X, Y, Z. Okay, means it will be like 1, 2, third input signal. The first one will be X. Okay, second one will be Y. Third input signal will be Z. So output will be X plus Y plus Z bar. Yes, this is a NOR gate. See here, what are the combinations? Total 8 combinations are there, because total how many input signals are there? 3. So means binary digits I can use 0 and 1. Total in the sense 3 input signals, 2 to the power 3. So total how much I can provide combinations? 8 combinations I can provide. So when this says 8, means start counting from 0 to 8 numbers, means 0, 1, 2, 3, 4, 5, 6, 7. Yes, from 0 to 7 decimal numbers, just write down them in the binary forms. Okay, now we'll see. This thing we have discussed in the last year. If anybody is not getting, you can ask me. Okay, now the first combination is 0, 0, 0. See, what is the output for 0, 0, 0 combination? The output is 1. Okay, for all the remaining combinations the output is 0. Means what? If any one of the input signal is 1, then the output will be 0. Only if and if all the input signals are 0, then only the output signal is 1. Otherwise it will be 0 only. Yes, so this is about the NOR gate. So here question can be asked, write the logic symbol for NOR gate. You have to write the symbol. If they ask for a 2 input NOR gate, write this truth table which is there on the left side. If they ask for a 3 input NOR signal, write which is there on the right side. So what is the behavior of this gate? This gate has 2 or more input signals but produces how much output signal? How many output signal? It produces only one output signal. How is the behavior of this gate? That is, if all the inputs are low, then only the output signal will be high. Otherwise, the output signal will be low. Yes, I hope this is clear. Now, we will see the next derived gate, that is NAND. Guess which kind of a gate it may be? Anybody? Okay. So NAND gate is nothing but it is also a combination. This gate is also derived from basic gates only. Which are those? You can see here. This is AND. Yes, AND and N means it is a combination of NOT gate and a AND gate. So how is the logic structure of this? Logic diagram of this. This is, since this is a combination of AND and a NOT gate. This is nothing but an AND gate, right? So if I place here a bubble, this becomes a NAND gate. Okay, so here the behavior of this NAND gate is exactly opposite of the AND gate. Okay, what was the AND gate? When the output signal was high there, in the AND gate we saw if both the input signals are high, then only the output was high, otherwise it was low. Yes, but here what happens? Here what happens? It is exactly opposite of AND. Oh yes. Okay, let's see what is this NAND gate. The NAND gate has 2 or more input signals. This gate can also has 2 or more input signals, but it also produces how many output signal? Only one output signal. Yes. So then how is the behavior of this gate? This gate behavior is, if all the input signals are high, okay, see, one input signal is X, that is 1, another input signal is high, means both input signals are high, then only the output is low. Yes, this is opposite of AND gate. If both the input signals are high, then only the output is low. Okay, what about the other combinations then? If any one of the input signal is low, then what will be the output? Output signal will be high. Yes, similarly, if both are low, then also the output signal will be high. Yes, this is simply opposite of your AND gate behavior. Yes, so what is an AND gate? It is a gate which has two or more input signals but only one output signals. And how is the behavior? If all the input signals are 1, that is high, then only the output signal will be 0 or low. Yes, okay. Now, as I said, it is a combination of NOT and AND gate. Okay, or it is also called as inverted AND gate. Okay, this means AND gate is always followed by NOT gate to give the NAND gate. Yes, I had just drawn first the AND gate. After that, I had drawn a bubble. A bubble is nothing but it is representing a NOT gate. Yes. So how can we represent the symbol of NAND gate? That is X logical multiplication y bar. So the diagram, symbolic diagram is like this. Okay. Now see the truth table. So here X and Y are the inputs. Yes. So this is X. Yes. And this is Y. So what will be the output? Output will be X logical multiplication Y. Means what? This will be the AND gate. If I put here complement or a bar, then it will become what? It will become a NAND gate. Okay. Now see the truth table for this two input NAND gate. What is the behavior? If all the inputs are high, then the output produced is 0. See here, when all the inputs are high, in the last row, here X is high, that is 1, Y is also high, that is 1. So what is the output there? That's this time the output is 0. Yes. Now in the first row, both inputs are low, that is 0. In the second, one of the input is 0. In the third, this one of the input is 0. That time what is the output? The output is 1, that is high. Yes. Now similarly see for the 3 input NAND gate. So which are those 3 inputs? That is another one we can add Z. So this will become what? X logical multiplication Y logical multiplication bar or a complement. Okay, so the combinations are here 8, 2 because 2 to the power 3 is 8. Okay, so now see the behavior here. Here also in the last row, in the last input combination only, we have all the ones. X is 1, Y is 1 and Z is 1 here. So that time what is the output? The output is 0. Yes. Now see all the above 7. Here we have 0 in any of the inputs. Here also we have 0. Third also 0. Fourth is also 0. In fifth also we have 2 zeros. Sixth also we have 0. Seventh also we have a 0 here. Yes. So during those time, what is output? Output is 1. Yes, so understood the behavior. So NAND gate is exactly opposite of AND gate. So it is also called as an inverted AND gate. So this has 2 or more input signals, but it produces only one output signal. And if all of the input signals are high, then only the output produced will be 0 or low. Otherwise, if any one of the input signal is 0, then the output will be high. Yes. So now we saw 2 derived gates. One is NOR, another one is NAND. Okay. So now moving on to the third derived gate, that is XOR gate. XOR gate full form or expansion is exclusive OR gate. This is also called as exclusive OR gate. Okay. So see how is the behavior here. This gate can also accept 2 or more input signals, but this gate is also producing how many output signals? It is also producing only one output signal. Yes, but see what is the behavior of this gate? The behavior is the output is 0. When the output will be 0? If there are even number of ones in the inputs. Okay. If there are even number of ones in the input. Even number of ones in the sense, Number of ones can be 0, or number of ones can be 2, or number of ones can be 4 in the input signals. If such kind of even numbers are there for ones in the input signals, then the output will be 0. Okay, then the output is 1 if there are odd number of ones in the input signals. Okay, so how can we represent this XOR here operation? So this is the symbol for this. What is that symbol? A XOR B. This is for 2 input XOR gate. So here see the last gate, we have 4 input AND gates, right? So first one if I say A, second if I take B, third if I take C, fourth if I take D, what will be the XOR symbol? That is A XOR B, sorry, A XOR B XOR C XOR D, like this. Okay, now see the truth table. As is the behavior of this gate is what? The output signal will be 0. Yes, X and Y are the 2 input signals. So consider here, this is X and this is Y. These are the 2 input signals. Yes, so output of this, consider it as a Z. Okay, so this Z output signal will be 0 if and only if in the inputs we have even number of ones. See in the first row, see X is a 0, X, Y is also 0. Yes, so how many ones are there here? 1 is not there. Yes, means one is there how many times? It is there in 0 times. That time what is the output? The output will be 0. Yes. Now in the second one, see here X value is, X input is 0, Y input value is 1. So what is the output? That is 1. Yes, why it is 1? Because the output is 1 if there are odd number of ones in the input. One input has, means high voltage input has appeared how many times here in the second row? Input has appeared for 1 time. So see in the third line here 1 is appeared for 1 time, that is for X. Y has input 0. Yes, so here high voltage, that is 1, has appeared 1 time. In the third row also that has appeared for 1 time. So the output is 1 for this. Yes, I hope you are getting. So what is the behavior of this XOR gate? So XOR gate, it can accept either 2 or more input signals, but it is going to produce always a single output. Yes, the output is 0 if there are even number of ones in the input signal. So, even number of ones in the sense when all the input signals are 0, then the output signal is 0, or if any 2 input signals are 1 or even number of input signals are high or 1, then the output signal will be 0. Yes, now if we have odd number of ones, here 1 has appeared 1 time, here 1 has appeared 1 time, 1 time, 1 is nothing but odd number, right? Yes, so that time the output is 1. Okay, so you have to remember these behaviors. Now see the truth table for a 3 input XOR gate. 3 inputs are which one? X, Y and Z. Okay, F is nothing but X XOR Y XOR Z output it is. Okay, now see the first row. Here how many ones are there? 0, 0, 0. There is no one in the input signal, right? So that time what will be the output? The output will be 0. Here they have mentioned the output is 0 if there are even number of ones in the input. If no ones are there in the input, means consider this as a even number of ones only. Okay, now see the second one. See the second one, this one, how many ones are there? X has value 0, Y has input value 0, Z has input value 1. Yes, so X is 0, Y is 0, Z 1. So 1 has appeared how many times? That has appeared 1 time. 1 time in the sense that has appeared odd number of times. Yes, so that time what is the output? Output is 1. Okay, because the behavior is The output is 1 if there are odd number of ones in the inputs. Yes. Okay, now in the third row, see, x has a value 0, y has a value 1, z has a value, input signal 0. Here also 1 has appeared how many times? Here also 1 has appeared 1 time. That is odd number of times. Okay, so the output is 1. Yes. So now see this fourth row. X has input value 0, y has input value 1, z has input value 1. What is the combination? 0, 1, 1. So 1 has appeared here how many times? 2 times. Yes, 1, 1, that is a high voltage that has appeared 2 times. When the value 1 has appeared 2 times means 2 is a even number. That 1 has appeared even number of times, that is 2 times. So that time what is output? Output is 0. Yes, I hope you are getting. When 1 has appeared for even number of times, that time the output will be 0. If the input signal 1 is appeared odd number of times, that time the output will be odd, that is 1. Okay, now see the fifth one. Okay, here 1 has appeared 1 time, y value is 0, z value is 0. Means what is the combination? 1, 0, 0. Yes, 1, 0, 0. How many times the input signal is high here? 1 time only. So 1 is a odd number of times. So that time the output is 1. Okay, now next see, x value is 1, y value is 0, z value is 1. Means 1 has appeared how many times here? 2 times. That is combination is 1, 0, 1. 1, 0, 1. So 1, 0, in this 1, 0, 1, 1 has appeared how many times? 2 times. 2 times in the sense it is even number. Yes, so that time the output is 0. Okay, now see the next one here. This is x value is 1, y value is 1, z value is 0. Combination is 1, 1, 0. Yes, so the 1 has appeared how many times here? 2 times. 1, 1, 0, right? So 1 has appeared 2 times. 2 times in the sense it is a even number. So now what will be the output? The output will be 0. Yes, because 1 has appeared even number of times. Yes, now see the last combination of this table. X value is high, that is 1, y value is also 1, z input signal value is also 1. So that time what is the output signal? Output signal is 1. Why? Because 1 has appeared 3 times. 3 is a odd number, right? 3 is odd number. 1 input signal 1 has appeared 3 times. 3 is a odd number. So that time the output will be 1. Okay, so hope you are getting. What is this XOR gate? This is also one of the derived gate. Full form is exclusive OR gate. Yes, so this gate also accepts 2 or more input signals and always produces only one output signal. What is the behavior of this gate? The output is 0 if there are even number of ones in the inputs. Yes, and the output is 1 if there are odd number of ones in the inputs. Okay, this is the third derived gate we saw. Now moving on to the fourth derived gate, that is XNOR gate. That is XNOR gate, or we call it as a exclusive NOR gate. Full form is exclusive NOR gate. This gate, see here what is there? It is a combination of XNOR and NOT gate. Yes, so it is exactly opposite of XNOR gate. Okay, see, this gate can also accept 2 or more input signals. Here we have given 2 input signals for this diagram, X and Y. And what will be the output signal? Output signal will be X XNOR Y. Okay, X XNOR Y. Yes, see this, what is the behavior of this gate? X XNOR produces out 1 or high as output when the input combination has even number of ones. When the input combination has even number of ones, it is exactly opposite of XOR gate, I am telling. So if we have here even number of ones, suppose 1 1 0 like this, then only we are going to get output signal as 1. Or when all the inputs are 0. Okay, when all the inputs are either 0, all the inputs has to be 0, or in the inputs combination of ones should be even. Yes, then only the output signal will be high. If we have odd number of ones in the input signals, then we are not going to get output as 1. That time we are going to get output as a low for odd number of ones. Yes, so this XNOR gate is nothing but it is a complement of XOR gate. This is a complement of XOR gate. See the diagram. How can we draw? We have here one OR gate. Yes, so behind the OR gate there is one line. Okay, that we have to include because that is representing a XOR gate. Yes, so in front of this OR gate we have an bubble. Yes, that bubble is representing NOT gate. So this is a combination of XOR gate and a NOT gate, and this is exactly the complement or opposite of XOR gate. Now we will see with the help of truth tables what is the behavior of this gate. First we will see with the 2 input XOR gate. See here, 2 inputs are which one? We have X is input, Y is also one of the input, and the F is nothing but a output function or say output signal. Okay, so what is the behavior here? This gate produces 1 as input when input combination has even number of ones. 1 is even number of ones. Where are the even number of ones are there? This one. Yes, so here X is 1, Y is 1, means one input signal has appeared how many times? 2 times. That is even number of times. So that time what is the output? Output is 1. Yes, or another time, or when all the inputs are zeros. So when all the inputs are zeros, see the first row, X is 0 and Y is 0 here. Yes, that time is also what will be the output? The output will be 1 or high. Yes, so if we have odd number of ones in the input signals, that time the output will be what? Output will be 0. Yes, for even number of ones the output will be high for XNOR gate. For odd number of ones the output will be low for XNOR gate. Yes, I hope you are getting what I am trying to say. Now we will see the XNOR gate behavior for the 3 input XNOR gate. Okay, so which are those 3 inputs here? One is X, another is Y, another is Z. So what is the output signal here? The output signal is F. Okay, now see the combinations. First one is 0 0 0, means all the input signals are 0. So all the input signals are 0. That time what has to be the output? Output should be 1. Yes, okay. Now see the second combination. First input is 0, second is 0, third is 1. 0 0 1. So here here the signal 1, that is signal high, has appeared how many times? 1 time. 1 time in the sense that is appeared for odd number of times. So that time the output will be 0. Yes, now the next combination is 0 1 1. 0 1 0. 0 1 0. Here also input signal 1, that is high, has appeared how many times? It has appeared only 1 time, means it has appeared odd number of times. So that time what will be the output? Output will be 0. Yes, now see the next one. Input signal X is 0, Y is 1 and Z is 1. Yes, so here 1 input signal 1 has appeared how many times? 0 1 1 1 1 2 times, right? 1 is there 2 times, that is even number of times. So that time what is the output? That time the output will be 1, high. Okay, now the next one, see 1 0 0 1 0 0. 1 has appeared how many times? 1 has appeared here odd number of times. Yes, so when 1 has appeared odd number of times, the output will be low, that is 0. Yes, now the next combination is 1 0 1 1 0 1 0 1, right? Okay, now see the next combination is, sorry for disturbance, next combination is 1 0 1. So here 1 has appeared how many times? So here is 1, here is 1. 1 is appeared for 2 number of times, that is even number of times. So what will be the output? Output will be high, that is 1. Yes, the next combination is 1 1 0. Here also 1 has appeared how many times? The input signal 1 has appeared, that is high has appeared 2 times, that is also even number of times. So what will be the output? The output will be 1, that is high. Now see the last combination. Here x value is 1, y value is 1 and z value is 1. Yes, x value is 1, y value is 1 and z value is 1. So 1 has appeared how many times? This 1 has appeared 3 times. 3 in the sense it is odd number or even number? 3 is odd number, right? Yes, so when we have odd number of ones, that time the output will be 0. Yes, I hope you are getting. So what is this XNOR gate? Basically, this XNOR gate is also one of the derived gate which accepts 2 or more input signals and produces only one output signal. Okay, so what is the behavior of this gate? This gate produces output as high or 1 when all the input when it has input combinations even number of ones, or when all the inputs are zeros, that time only it is going to produce output as 1. If we have even odd number of ones in the input, that time it is going to produce output as 0. Yes, so the students, till now what we saw from the beginning, I'll tell you from this chapter beginning, we saw what is a logic gate, types of logic gates, that is basic and derived. In the basic we had three types which are those not, or, and. We saw the explanation of those. Yes, so next in this session I started with the derived gates. In the derived gates we have 4 gates, so we have done with explanation of all 4. So here question can be asked, any one of the gate symbol, any one of the gate logic symbol is compulsory question, that can be asked for 1 mark. Okay, and they can also ask you explain the gate. Any gate can be asked for explanation. Explain explain NOR gate, NAND gate, AND gate, OR gate, NOT gate, XNOR gate. Any gate can be asked for the explanation. That time what you need to do, you have to write what should be the input, what should be the output. When you give input as odd number, even number, what will be the output? Okay, high or low, like that, and write the logic symbol and write the truth table. Okay, if you have any doubts you can ask me. So now remaining part I will continue in the next session. Okay, thank you.